We're going to go ahead and get started. My name is Gary Rasp. I'm the Communications Director at the Energy Institute. Many of you know that Varun is out of the country this week, and he asked me to fill in for him and kick things off. I'm here to introduce our speaker tonight, Dr. Ray Orbach, who's the Director of the Energy Institute. And he's going to be talking about one of the more controversial issues. You've heard some about this semester, climate change, global warming, whichever you prefer. Dr. Orbach, before coming to UT to found the Energy Institute a little over 2 years ago, was the first Undersecretary of Science at the Department of Energy, where he was the chief scientist and reported to the Department of Energy and oversaw the nation's national laboratories and helped make the transfer of their research to the global marketplace. So he was there for a number of years, actually starting as the director of the Office of Science prior to his appointment as Undersecretary of Science. Prior to that, he was a chancellor at the University of California, Riverside, where he led tremendous growth at that university and was acclaimed for his work in promoting diversity and opportunities for students. He's a noted physicist and scholar, has published well over 200 papers, and I think you'll find his remarks very interesting tonight. At the Institute, just real quickly, for those of you who haven't read up on what we do, Dr. Auerbach builds teams, interdisciplinary teams, from faculty across campus to take on some of the more compelling energy issues facing our society today. And so, for example, you've heard about hydraulic fracturing of shale gas. We're studying that right now. He's leading a team that has its final report due in early next year. And he's also leading a team also from across campus that will produce a report, again, early next year on unconventional natural gas and oil. Also doing research into the conversion of sunlight into hydrogen, large-scale electrical energy storage, all over the place, across the spectrum of energy issues. So tonight, again, I think you'll be very pleased to hear what he has to say. This is a very, very controversial issue. I don't have to tell you that. And it says to me, it's a great illustration of how he not only has a passion for science, but the courage to tackle these really challenging issues and stand up and say what he thinks about them. So without further ado, please help me welcome Dr. Ray Orbach.
Thank you, Jay. Well, thank you. Thank you very much. And first, I'd like to thank all of you for participating in the symposium this semester. This was an idea that Professor Rye suggested when he first came here and is meant to bring the campus together around energy issues. What I'll be talking about today is in some way a bookend, because your first talk was on climate issues, and I'll be talking about that today. I just want to thank all of you for putting up with us as we attempt this experiment. We'll be continuing next semester. We already have some very exciting speakers lined up, and I hope that you'll continue in this relationship. My purpose today is to talk about sustainability and to, first of all, give you sort of an introduction as to why, and then some things that we can do to maintain our planet Earth, our spaceship Earth, as Buckminster Fuller has called it, into the future. You are the generation that will be charged with these responsibilities. And so I thought it would be of help to tell you some of the things that can be done to preserve our globe for human life and development. I've written up the talk in a paper which has just appeared in Reports on Progress in Physics. It's called a perspective article. It's not meant to be an original research. Rather, it's my view, my personal view, of climate issues and what we might do about it, and it has the same title that you see here. I've also, because the slides are somewhat complicated, I've printed up all of the slides that you have in front of you so that you don't have to write anything down. The first thing that one has to consider is energy usage on the Earth. This is taken from the annual report, the BP Energy Outlook, out to 2030. You can get it on the web if you want to go to their website. And what it indicates is this line is 2010, and each of these different colors represents a different source of energy. And you will see that coal is projected to increase in use, not decrease. The same is true of oil and of gas. And the most important part of this curve is the relative size of the contributions to our energy budget. They have renewables up on top, which includes biofuels. This is a projection that BP made, and I think there's still a question as to whether that projection is accurate. I don't have to tell you what's been happening in the United States, and in fact, if you watch today the hearing that Secretary Chu was a participant in, a leader in, you'll have an idea of the debate, national debate, over renewables. In any case, it's a very modest amount as compared to other energy sources. And this is a 20-year period. The reason it's important is 2020 is important. Our president went to Copenhagen and signed a statement that we would reduce our CO2 emissions by 17% relative to 2005 by 2020. Well, we're almost at 2012. There's only 8 years left, and you'll see what our CO2 production looks like, and obviously it's related to these bars that you see on the right. People talk about hydrocarbons as though they're bad business, and this is up to you to formulate your own opinions, but you saw the curve, and in my view, we've got to deal with coal and oil and natural gas. They are the drivers of the global energy portfolio, and this is something that was put together by Tad Pachek, who's chair of the Petroleum and Geosystems Engineering Department. It's interesting that wind across the United States is roughly responsible for 6 days of electricity, biomass roughly 5 days, geothermal 1 day, solar photovoltaics about an hour. And so you've got 354 days out of the year that you've got to find other sources. And of course, they're the hydrocarbon sources. And you can argue that they have a profound effect on the globe, and that's what I will be arguing, but you're not going to do away with them. So the question is, what can you do about them? This is a plot of CO2 production globally, and as you will see, with the increase in coal, there's a marked increase in CO2 emissions. If you want to remember some numbers, and these are very crude, if you call coal emissions of CO2 100%, then oil is about 80%, and natural gas is about 50%. So roughly speaking, natural gas emits CO2 for the same amount of energy at something like half of what coal burning would do. It's better than that. If you're looking at electricity, the efficiency of combined cycles actually makes it about 3 times as less CO2 than coal-fired power plants of the usual sort. The thing that one has to recognize is that the OECD countries are projected to decrease the amount of CO2 they produce over the next 20 years. But look at the non-OECD countries. Their CO2 production will go up sharply and way, way overcompensating for any reduction of the OECD output. And you know which countries there are. And the question is, can we deal with that emissions and still allow them to develop as they want to develop over this 20 years? This is a slide that's very hard to read, but it's somewhat chilling. I don't know how many of you are economics majors, but there was an economist back in, of all things, 1885 named Jevons, who formulated Jevons Rule. and that is improving economic efficiency enables the creation of more new energy uses than energy savings. The net consequence is to increase the rate of resource depletion. Jevons Rule has proven to be remarkably stable, unfortunately, and here I plot the CO2 emissions and the total energy usage as a function of 1970 to 2005, 100 years later than Jevons lived. And you will see that they track each other. That's an important statement because it means that clean energy sources are not replacing any of fossil fuel use. Now, I'm not arguing this is the right thing that should happen. I'm just telling you what our statistics appear to show. You will see that there is an increase in in efficiency of our uses, but it's a very modest increase in comparison to the CO2 and energy increase. And notice the GDP increase on the same scale. And of course, this energy and CO2 emissions are linked to GDP growth. This is perhaps even more, and I don't mean to be too discouraging, but when I was first introduced to this issue of CO2 concentrations in the atmosphere, the total CO2 concentration target was 450 ppm. That is parts per million by volume in the atmosphere. It's now 385 or 386 parts per million. The historical value for at least 2 millennia has been around 280 parts per million. And the problem is that it continues to increase. For example, if you just had the same amount of CO2 emissions, if you kept them and kept them constant, the actual CO2 concentrations in the atmosphere would continue to increase. And this is because of the dynamics associated with warming and the effect of CO2 on the global atmosphere and oceans and land. The only way to actually reach a stable concentration, and you'll see this is around 600 ppm on this plot, is to reduce CO2 emissions by 80%, starting, for example, as we did here, in 2050. You will remember that 80%. That was part of the Copenhagen statement. They said that the target would be, and they didn't tell you how, that we would reduce CO2 emissions by 80% by 2050. And indeed, the European Union has that as its target. That's where it comes from. You have to reduce emissions by about that amount in order to keep the CO2 concentration in the atmosphere stable. Now, who cares about the CO2 concentration in the atmosphere? We now know, or at least we believe, that it leads to a warming of the atmosphere, and from that, a warming of our globe. These are very rough numbers, but if you hold the CO2 concentration at somewhere around 550, it translates to about a 2 degrees Celsius increase in temperature by the end of the century, by 2100, which would give you a sea level rise, again now, these are rough numbers, of something like 0.8 of a meter. That may not sound high to you, but that's actually a fair amount. The difficulty, of course, is that as you start to go beyond 550, and you see what may happen if you don't control CO2, those numbers go up. There was a recent talk in Venice. Venice has just built a seawall because they have a terrible problem with subsidence and sea level rise that will account for a 70-centimeter increase in sea level. And one of the speakers there said his calculations indicate that it'll be more like 2 meters. 2 meters of sea level rise will create what we call climate refugees, because there's a large portion of our Earth that are heavily populated where a 2-meter sea level rise would literally eliminate the land on which they live. not to mention what may happen here in Texas, Corpus Christi and elsewhere, where it's actually fairly close to sea level. And indeed, one of the issues that I think we're going to have to deal with as a society is adaptation. You will see why as I go through the presentation. The next question is, are we warming? And this is taken from the Bulletin of the American Meteorological Society. And I don't know how many of you read the Wall Street Journal, but you will, if you do and you read the letters, you'll see that I've written 2 letters on this, on how you actually determine what the increase in temperature of the surface of the Earth has been on a global scale. They argued that, first of all, in 1980, there was a step function increase. It was the warmest decade on record at the time. And that means over millennia. And indeed, if you go back and look at the simulations and also the measurements, and they weren't terribly good in the year 1000, you will find that this indeed was the hottest time ever. The next decade found a higher average temperature than the previous decade, and every year was warmer than the average of the previous decade. And just last year, they came out with the decadal numbers for the year 2000 to 2009, and again, every year was warmer than the average of the year before, and it was even, you can see by yourself that it was hotter. Now, you will read in the newspapers and in magazines that, in fact, there isn't heating. That, in fact, if anything, there's cooling in that decade. Be careful. What people sometimes do is to cherry pick. There are oscillations in the temperature readings, and what you really need to do is what's called a moving average. If any of you take a look at the Dow Jones Industrial Average, they move all over the place, literally. But the people who are interested in long-term behavior do a moving average over some period of time. And we now know that in order to get a signal-to-noise ratio of about 4, you have to average over about 17 years. So it is possible to cherry-pick these rapidly oscillating numbers and come up with almost any number you like. But if you do the average, this is what you find. Okay, the next question is, what happened in 1980? Why all of a sudden are we warming? And the answer is nothing. It turns out that equilibrium warming can more or less double the instantaneous increase in temperature. But there's other factors that affect our global temperature, and in particular the oceans. The oceans, especially the surface, maybe top 100 meters, have a huge heat capacity as compared to the atmosphere. And so as the atmosphere warms, it takes a while for the ocean to respond. And indeed, if you look at the simulations, you will see that there's been a very gradual warming since 1880, and then it suddenly takes off in 1980. So, okay, what happened in 1880? Why did that consequence mean that today we are seeing increases in temperature? What was it? Well, you can talk loosely about the Industrial Revolution, and here actually in our history department we have some wonderful faculty who have studied the Industrial Revolution, and that's where some of these slides came from. It turns out that in 1880, the use of coal was such that it exceeded the energy from wood and went on to continuously increase. And this was because of the Industrial Revolution that started in Britain maybe a century before. But as I understand it, Britain became so wealthy that it exported the Industrial Revolution to the continent and even to South America and Asia. And that was the reason for this sharp increase around 1880. You can also on the same plot, this is from a marvelous book by Smell, look at the global use of fuel for energy as a function of year, and 1880 is about here. So things started to take off. There are reasons why it happened first in Britain and not on the continent. We can go into that if you're interested. But it's interesting, again, on the same plot, to take a look at the CO2 concentrations in the atmosphere. These are from ice core measurements, and then the red is actually from atmospheric measurements. The first thing that's interesting is that they sit on top of one another. The second thing is take a look at when it really takes off. It's 1880. Now, this is circumstantial, and indeed, as I said, the simulations appear to agree with this, and it's really trying to tell you something, at least it tells me something, namely that CO2 is increasing and continuing to do so, and it's related to our global energy usage. So what can we do about it? Well, the purpose of the talk is really not to dwell on the fact that the Earth is warming. It's rather, how can we deal with what we're finding? And I'm going to talk about 3 different things that actually are taking place here on the campus that will, in my view, deal with CO2 emissions and have a hope, and they won't do it by themselves, but are examples of how we can accommodate ourselves to increase uses of energy and reduction of CO2. The first thing I'm going to focus on is coal. It is the chief culprit. We are estimating by 2030 to increase to 2.3 gigatons per year of emissions of CO2 from coal. By the way, remember the Copenhagen Accord? We were going to reduce by 17% to 2005. I don't know if anyone believes that, and if you read the papers, you saw about 2 weeks ago that Japan has stated that it can no longer meet the Kyoto Accords for Japan. And that's the Kyoto Accords about which they were so proud. And it's simply a question of your economy and the role that energy plays within it. The problem with coal, which is really responsible for about half of our electricity in the United States, is that the emissions from coal-fired power plants are in the form of CO2 contained in the flue gas. The flue gas is relatively dilute, it's about 12% of CO2, and it's hard to capture it. And if you simply use our conventional means for capturing CO2 and assume that you can sequester it from the flue gas in coal-fired power plants, it takes about 1/3 of the power plant's energy. And it's simply not economical. In an unregulated environment such that we have in Texas, if you try to sell ERCOT electricity at 1/3 more than your competitors, guess whose electricity ERCOT is going to buy? So economically, it just doesn't work. Now you can say, well, what about a price on carbon? Maybe we could tax it. Maybe we could have a cap and trade. Well, there's a huge argument about how much it actually costs to capture CO2 from a coal-fired power plant. Gary Rochelle, who's a distinguished professor here in chemical engineering, argues it's between $50 and $75 a ton. Now, there are others who argue that it's 80 to 100. What price are you going to put on CO2? The Australians have just put a price of around $20 a ton. In Europe, it's been moving all over the place, but it's never gone above 20. It's down, I think, somewhere around $15 a ton. The point is that no economy can survive with $50 to $75 a ton as the price of carbon. So is there any way to bring down the cost of carbon capture from coal-fired power plants? The next slide will give you a sense of what the problem is. This is CO2 in terms of millions of metric tons. From electric power, the black is from coal. You'll notice that transportation, which is gasoline, oil primarily, has about the same CO2 emissions this is for the United States, by the way, as electricity from coal. And so if we were to simply eliminate the CO2 from coal, we'd still have about half of the CO2 emissions that we currently have. I think most of you heard Jim Marston's talk last week. There are ways that one can approach a reduction of CO2 from transportation, but we won't go into them here. This is the estimate of CO2 emissions out to 2030 for the United States. And indeed, there was a dip around 2008, and that was due, of course, to the recession. But you see that it steadily increases with really no hope of ever getting back to the 2005 level. This is from the Energy Information Administration. So it makes a difference if we can do something about coal from coal-fired power plants. Well, the Petroleum and Geosystems Engineering Department on our campus and the Chemical Engineering Department have come up with a very clever way of offsetting the cost of capturing CO2 from coal-fired power plants. The way that CO2 capture works is to use a liquid which is ammonia-based. It's called an amine liquid. And what you do is you run the flue gas through that liquid when it's cold. And there's literally a mechanical capture. It's a complicated organic material. But there's a mechanical capture of the CO2 by the amine liquid. And then what you do is you circulate that liquid and you heat it up, usually with steam. And that's what costs you your energy. When you heat it up, the cage, this is again very crude, opens up, the CO2 comes off, it's a pure stream, and you've got it for sequestration. But the cost of heating up that amine liquid is what's costing you your energy. Is there any way to offset it? Well, the conventional way has no offset. It's pure cost. You simply take that CO2 and pump it in the ground. The difficulty is that the ground is not water. These are typically, when you pump it into an aquifer, it's a sandstone or a carbonate material, and you actually get a back pressure. Our simulations have shown you can't pump CO2 into these aquifers for more than about 6 months. So not only is it expensive, it doesn't work. But those aquifers, especially along the coast of Texas, but actually across the country, are rich in methane. Turns out that the aquifer under us, extending out into the Gulf, has about 6,000 trillion cubic feet of methane. And back in 1985, there were experiments actually about producing natural gas from these aquifers. They're still there, and they're loaded with methane. It's not very soluble, but there's a lot of liquid. And they're hot. They're about 300 degrees Fahrenheit. So you have an option then of using the heat and the methane to offset the cost. And that's really what we've come up with here, Steve Bryant and Gary Pope and Gary Rochelle. This is a picture of how it works. This is, of course, very schematic. Here is your aquifer. The red means it's hot. And what you do is you bring up that liquid to the surface. These are geothermal, geopressured reservoirs, and so they typically are about 12,000 psi. They're down about 10,000 feet. You bring them up to the surface, you depressurize it to, say, 1,000 psi, and the methane, some methane comes off. You run that, it's hot, through a heat exchanger to offset the cost of that CO2 capture that we talked about. And so now you have a cool brine, but still loaded with methane. In the meantime, the CO2 that you've extracted can be inserted at the surface into the liquid. Turns out that CO2 is 10 times more soluble than methane in water or in these liquids. And you get a phase separation. Those of you who remember your ternary phase diagrams will recall that when you have something 10 times as concentrated or as soluble, you get a burst, you get a phase separation, and almost pure methane comes out. And so by inserting the CO2 at the surface, you've extracted the methane from the two sources, and it's worth something. You can either replace the energy that you've lost in the power plant, or you can sell it. But what's even better is you then have a CO2 saturated liquid, and you have gravity helping you. It's incompressible, and so this is a closed system for the liquid. We've done simulations, and you have the numbers in front of you. And it's a little hard to read, but the combination of the value of the methane, now we took $6 a million BTU. That's a little high, but there are people who believe that it will be in that range not too long in the future. And the amount from just a 100-degree drop in the temperature of the aquifer summed to about $31 a ton. Now, these are very conservative figures, but what they suggest is that there's an offset of the cost. Both the heat, the geothermal, if you like, and the value of the methane are such that they reduce the net cost. Now, it's not 100%, but we're getting there. And as I said, these are very crude. Furthermore, Professor Rochelle only took us down to 200. He could have done it to 150. There are ways of enhancing even this. The point is that by using chemical properties and thermal properties, we can gain back some of the energy that we needed in order to capture the CO2. We're teaming up with LCRA and NRG Energy to actually try this out. First, to do the calculations by themselves to see whether we're right, and then to actually try this in the field itself. So that's one way of reducing the cost of carbon capture. Are there other methods that we can develop here, for example, at UT Austin? And this one is one that's literally being developed as we speak by Professor Alan Bard and by Professor Buddy Mullins. Professor Bard is in chemistry. Professor Mullins is both in chemistry and chemical engineering. And crudely speaking, it's artificial photosynthesis. We know that plants can take sunlight and water and CO2 and produce their fuel, the ATP that plants use to grow. Plants are not very efficient. They're only about 1%. If we could do what plants do, we could take CO2 and make fuel. Now, the problem is we haven't figured out how to do it. We do not know how to reduce CO2 efficiently in order to turn that into a liquid fuel. So what we've been looking at is water. Can we split water into hydrogen and oxygen directly as a plant would? That is, can we take sunlight and water and end up with hydrogen? That turns out to be very important. As you may know, the octane rating in your gasoline is really controlled by the hydrogen that you substitute for the oxygen in the oil that they work with in the refineries. A typical refinery will use about 1 billion cubic feet of hydrogen a day. And the way they produce the hydrogen is by reforming natural gas. So for every 4 molecules of hydrogen, you get a CO2 molecule. If we could give refineries hydrogen without CO2, we would reduce our carbon footprint by 30 to 40%. That's just refineries, not talking about other uses for hydrogen, for example, transportation, or for that matter, combustion in an electric generator. So how do we do it? This is a picture of a photoelectrochemical cell where sunlight comes in. You generate an electron-hole pair, and then the electronic band produces the hydrogen and the hole band the oxygen. The difficulty, of course, is finding the right band gap that absorbs the sunlight, and then something which is active photoelectrochemically. And it turns out that you can do it with platinum, but you're going to have to cover a large part of the state of Texas with platinum if you want to use it. And so what Professor Bard has been working with are inexpensive transition metal oxides. Now, this is almost combinatorial chemistry. What he does is to, for example, take small amounts of cadmium, indium, and bismuth and mix them together according to these concentrations. And then, with a little glass fiber, to see what their electrochemical activity is like. And what you find are little hot spots that tells you this remarkable combination of atoms gives you optimum electrochemistry. This is complicated because you've got 3 different materials that you're dealing with, and you're trying to find the right effective combination. It actually turns out to be even more interesting than that. If you add a 4th material to it, you add tin, you actually increase the photocurrent, which is somewhat counterintuitive because the electron and hole have to get to the surface to do activity, and so you're putting more junk into it, or another atom, and you increase that activity. What it means is it's not mean-free path. It means that there's probably shielding of some sort that enables the electrons and holes to get to the surface to do chemistry. Professor Mullins went one step further and developed thin films that are columnar in form. Can you see the columns? They can be as narrow as, I think my memory serves me, about 2 nanometers, or about 20 angstroms, and then relatively thick. So that what you do is you absorb the sunlight along the axis of the cylinder and do your chemistry at right angles. So the electron and hole don't have to travel very far. They're at 1%. They do just as plants do. But we need to get to about 10%. And it's better than a photocell. The typical photocell, if you just use electrolysis to produce hydrogen, is about 3% efficient. So we have a hope here of doing better. And at 10%, you've got something commercial. Well, can you get to 10% from 1%? That's what we're here for. And that's the kind of work that is going on in this area. The last one that I'll talk about has to do with electrical energy storage. And this is really the Achilles heel of wind power and even solar power. But it's also of coal and nuclear. We do not know how to store electricity efficiently at baseload levels. That is, at the level that utilities require. Batteries that we have today are very expensive, and they simply are not economical in large quantities. The reason we need this is that, as you know, in Texas at least, the wind blows at night. And of course, when we need it is in the afternoon during the day. Even solar, even on a clear day, will vary substantially. So you need something, first of all, to smooth that out, but also to make it available when you really need it. Solar is better than wind because when the sun shines, it's usually at the time when it's hot. But even coal-fired power plants and nuclear reactors do not like to be shut down or cycled. They like steady temperatures of their activity. And so it may be the case that you've got too much electricity coming at night from these sources, and you'd like to store it when it's needed during the day. Can you store it at base load? Well, Professor Goodenough in our mechanical engineering department is looking at what it would take to create a battery that could store electricity at base load. You need a high energy density, and I've listed all of the features that it would have to have here. The concept is a flow battery. You think about batteries, the energy of the battery when it's charged is contained in the cathode. What if you made the cathode a liquid? Then as you charge the battery at night when the wind is blowing, you then take that cathode, that liquid, and you store it in a tank. And then when you need it during the day, you have the liquid come back and the battery discharges. Well, once you store it in a tank, you can have an awfully big tank. And so a flow battery is capable of giving you the capacity that you need for baseload storage. Now, you want room temperature, so sodium sulfur battery is not going to be very helpful. And you want all of these other factors that are required. So what he's come up with is a couple that looks something like this. The redox is a iron water solution where the iron goes between iron 2 plus and 3 plus. And it has a solid lithium anode. And the action is right here between the anode and this liquid cathode, which is here. And this is just blowing this region up. You have here the liquid cathode. You have the anode here. Now, this is a liquid, so you'd better have a solid electrolyte. And that's the problem. In a solid electrolyte, can you get the conductivity of the lithium fast enough in order to be able to charge and recharge at a decent rate? Well, this is a research project, and Professor Goodenough is experimenting with, of all things, garnets, where by substitution you can get about 7% of the lithium into the garnet. It's a hard material. Will it work under cycling? We'll find out. But this is a challenge for any of you interested in materials science, to come up with the right electric potentials and also the right conductivity for the lithium ion. Alkali metal as the anode. In this case, it's iron cyanide as the aqueous solution. And then these are the primary attributes that it has to have for operation. So let me summarize. Fossil fuels as an energy source will be around for a while, certainly for the foreseeable future. Clean energy sources have not yet replaced any fossil fuel usage. CO2 production will increase at the same rate as energy increases, energy usage increases, and you saw what the projections are, at least over the next 20 years. We need to reduce CO2 emissions by 80% in order to stabilize atmospheric CO2 concentrations. Global warming appears to have a roughly 100, this is very approximate, 100-year time lag. So what we're experiencing now reflects what happened 100 years ago. And of course, it's somewhat chilling to think it really doesn't matter. For the next 100 years, remember that curve for the CO2? That's still there. And so what we're really talking about is the future of our planet. In the future, what can we do to offset the CO2 production? There are new technical developments, and we talked about 3 of them. There are others. But this is a challenge for us here at the university, for each of you, in terms of your own education and interests, because with it, we have a chance of reaching a sustainable Earth. Thank you.
Thank you very much, Dr. Orbach. That was great. As you can tell, he really presented sort of a dire outlook. Didn't pull his punches very much, but also provided some hope through the technology and science and research that's going on. So we've got about 15 minutes for questions. If I could ask someone maybe to help pass around the mic. Start right here.
Dr. Auerbach, with respect to carbon sequestration in saline aquifers, is much known about the permeability of those aquifers as related to flow rate needed to sequester the CO2 and with respect to other chemistry in the aquifer that might present engineering challenges?
The question is, do we know enough about the aquifers to be able to convince ourselves that we can actually put that much CO2 into them? The answer is yes. These aquifers are well studied and known. I mentioned that in 1985 there was actually 2 experiments to see if you could produce methane from these aquifers. It turned out that they failed on the market because the aquifer liquid is just awful stuff. It's hot, it's full of salt, and you can't put it in the ocean. It's too salty. So they had to re-inject it, and the cost of doing all that was just prohibitive. And so it never turned out to be economical, but they learned a lot. And if you look at your notes, you'll see that there's a little blue section in there somewhere when I talked about it, and all those numbers are there. It's a good eye chart. But if you look at the aquifer properties, that's on the left-hand side, we actually used in our simulations the properties of these aquifers. And we had a 1,000-foot separation between the injection and the production. It takes roughly 12 years. You remember in that picture, it was blue on the right and red on the left. That blue is full of CO2, and it's cool, and it's moving across. But you've got 12 years for that single injection to work. You can obviously do it at larger separations or have different wells that you're drilling. The important point is you're not transporting the CO2. In order to transport the CO2, you have to bring it into the supercritical stage. That takes energy. This is right at the power plant. So my thought was, if you're going to operate with coal, do it along the coast. That's where we have a lot of our power plants. And then use the aquifer below.
Other questions? Yes.
Thank you. I understand we have batteries specialists in AUT, but what about other storage systems, flywheels, compressing gas, other things?
There are indeed other ways of storing electricity. The flywheels are one. Compressed air is another. There's another of simply pumping water up a hill and then using it when you need it. To my knowledge, none of these are economical. We have a major flywheel program out at Pickle, and my understanding is they're about a factor of 5 off. They're not impossibly far, and that's with those things spinning around at, I think, 10,000 RPM. I mean, it's really quite remarkable if they hold together. They're not very big. They're only about that size. But none of them appear to be economical in that sense. And also, if you're dealing with compressed air and water, you want it where the wind is. You don't want to have to transmit it. And we don't have a lot of hills in West Texas where we have the wind, and so the water won't work. And I don't know about vast caverns where you can pump air into. To my knowledge, they just haven't developed to a point where they're useful. With the batteries, you can put them anywhere. And you want to put them right next to the source that's variable.
Other questions? Try this side of the room.
With regards to storage, what sort of capacity would we need with our existing electrical system for it to actually have an effect to mitigate our carbon dioxide production? Like where we could run the generation to charge the batteries to keep from going into peak utilization?
Well, it would depend on the power that you're dealing with and the amount of time. The wind is, I think, of the order of 10 gigawatts for Texas, and you want to do that over a 3 or 4 hour period. That's a lot of energy. It's a simple product of the two. I don't know the precise amount of volume that you would need for that, but that's the kind of calculation you would have to do.
Although I can see that the projection of the impact of renewables is pretty paltry compared to the fossil fuels, one category I don't see reflected here is the results of energy efficiency itself, which often is called the low-hanging fruit, meaning conversion to more effective technologies for existing electrical needs. Is energy efficiency still an opportunity to offset the continuing growth in fossil fuels?
Well, I mean, that's a question that's tough to answer. First of all, efficiency is good. We should try and be as efficient as we can. But Jevons says, and so far the evidence is there, that you can be more efficient, and it is important, but it doesn't offset the issue of the amount of fuel you use or the amount of energy you use. As I understand it, about half of Jevons Rule comes from the fact that if you are very efficient, you may end up heating more rooms in your house than you did before. We lived in Britain in the early 1960s. We heated one room. We had this miserable coal fire little heater. And then we got central heating, and we heated the whole house. And that, as I understand it, is only about half of Jevons Rule. There's other things that happen in terms of increased usage. There's nothing wrong with efficiency, and it's important that we do it. But you saw how the thing tracked.
Other questions?
So, with respect to your chart on the new clean energy sources, I guess I'm curious, and the fact that they're not replacing any fossil fuel use at this point, I'm curious whether you think that that's largely because they're new and they're such a small portion of the portfolio, or it's a kind of another Jevons paradox issue where we're getting new clean energy, but we're using fossil fuels even more. Do you have any insight into that? Is it kind of too early to tell?
Well, my understanding is that photovoltaics, for example, which is the way we produce electricity from solar, is of the order, the minimum I've heard, the goal is 15 cents a kilowatt hour. And that still factors of 5 more than coal. If you look at ERCOT's chart, I looked at that to see the sources. After all, we get a lot of sun in Texas. You find when it comes to solar, there's just a bar. They don't even put a number down. It's so small. Wind is heavily subsidized as well. On the other hand, it is coming down. The difficulty is storage. We just use, you remember this last summer, how hot it was, and ERCOT came very close to not having enough electricity for usage. It's a question of storage, in my view, to make wind a viable alternative. There are, of course, offshore winds as well as West Texas winds, and that has actually been very helpful because it's balanced. You don't have the swings in electricity. But still, you need the wind when it's not blowing. You need the electricity from wind when the wind isn't blowing. So in my view, it's a storage issue. Roger, you know more about this than I do. What is your view on that?
Well, I think it does come down to a lot to the storage issue. The prices are dropping dramatically. The current price that's being out there for solar PV is as low as 8.5 cents now.
Is that for the panel or for the total installation?
That's total retail, wholesale to the utility. That CPS Energy is getting bids on, for instance. So it is dropping fast. And I think there's a great new book out on Jevons paradox, by the way. It goes into it in great detail, and I think it is complicated. There's no doubt, though, that we're using more fossil fuels and we're going to continue to use more fossil fuels, even with efficiency. There are policies that can mitigate it if they're done correctly, but not completely offset it.
By the way, that's wonderful news that solar is down to 8.5 cents. That's still considerably higher than coal, but that's a lot better than 15, which is my number. Great.
Well, going back to that price of coal, of course, the negative externalities that we were discussing here are not priced into that, and that goes back to our unwillingness to make that commitment to pricing the coal. And you made a comment that no economy could withstand that $100 a ton addition. And I was just wondering where that comes from, why that you believe that to be the case. Because I would look at Texas specifically as an example where when we're generating power with coal, that it's very inexpensive, but it still represents a net dollar export in terms because we're importing the coal. Whereas a lot of the other sources, though more expensive at the wholesale level, that's money that recirculates within the local economy. So if you were to just draw a bubble around Texas and then could magically jack up the carbon sequestration price if we wanted to, and had other, could prevent the exportation of energy-intensive industry, for example, Texas would win with a carbon tax.
Yeah, there was
all the technologies that would double within the economic level.
there were a lot of ifs in what you suggested. First of all, we get the coal from Powder River Basin in Wyoming, and so when you talk about others, you're really still within the United States. I mean, it is internal. We're not importing it from abroad. The real issue for me is the lignite. There's a lot of coal around that's much worse than Powder River coal, and that is what you see going on in India and China. Remember the non-OECD countries producing? So they don't have Powder River coal. They're worse, but nevertheless, even the best coal we have, you saw the numbers when it came to the CO2. I don't think you can separate Texas from the United States, regardless of what the Constitution says.
We got time for a couple more questions.
Dr. Orbach, what about, say, the intersection of policy and technology with ideas such as Austin Energy's to create a second, perhaps, peak demand for energy by distributing hundreds of thousands of electric vehicles in the community and literally creating a second demand so that storage becomes less of an issue? I mean, what's the effect of that on mitigating the
People
need?
have argued that you could use electric cars as a storage facility at night. We're a long way from an economy with electric cars. I actually have a preference for natural gas. And you will hear, we're actually here at University of Texas at Austin in the process of developing natural gas powered transportation. We're a long way from doing it, but we're on to it. President Powers has created the President's Steering Committee for Sustainability on the campus. And 20% of Cap Metro's buses are leased by the university. So we are not a small player with regard to bus transportation in Austin. It is possible to transition to natural gas for buses. If you ever go to Washington, D.C. or L.A., you will see them. Those two cities are probably the most dysfunctional cities in the country. And they have natural gas-powered buses, but ours are still with diesel, and they smell. And I was astonished when I came to Austin because everyone told me how forward-looking the city was with regard to energy. And there is a technological innovation called metal organic frameworks, or MOFs, which are a material that's essentially all surface. And you can store at room temperature under standard conditions at roughly 80 atmospheres. About 40% of the density of the gas, compressed gas, as the liquid LNG would present in terms of energy density. And so BASF is now producing this commercially, and we're in line to be a prototype for application of a natural gas powered bus that would be fueled by compressed natural gas, not liquefied natural gas. It's a huge difference. And right now you can go out and buy a Honda Civic that's propelled by compressed natural gas. The problem is there's no trunk because it's all full of cylinders. But with MOFs, you can store 3 times the density of the gas itself. And so you can then reduce the volume of the cylinders in your car. Again, just as Gary said, it's a technological innovation that may change the name of the game. So my bets are on natural gas. Just one last thing that you might remember. What about cost? The cost is a factor of 6. You take the price of natural gas per million BTU, you multiply by 6, that's the cost of a barrel of oil at an equivalent energy. Okay? So natural gas today is actually less than $4 a million BTU. It's about 3.5. But let's call it 4 because I can do the sums. So that's $24 a barrel oil. That's a factor of 4 cheaper than gasoline or oil. Cap Metro spends $15 million a year on clean diesel. Factor of 4? I mean, that's a fair amount of cash that you save every year. And not to mention the fact that you saw the numbers that natural gas burns much cleaner than diesel, even clean diesel. So there are opportunities here for Austin, for our country. We have more natural gas now than anyone ever imagined 10 years ago. I don't know whether we have 100 years or 200 years, but a lot. And so we need to start thinking about ways of using these resources that will increase our efficiency and reduce CO2.
Okay, one last question. Dave?
So we think that natural gas certainly has its place. The well-to-wheel analysis that I've done, though, from a Daimler tool, shows that it's actually better as far as emissions and miles per gallon equivalent to take that natural gas and generate electricity, put it over high voltage lines and run it in an electric vehicle with a motor with 95% efficiency. But the battery cost for a bus, for example, will be kind of large. And so there's applications certainly where natural gas makes a difference and makes sense. But I'd be glad to send you those well-to-wheel analysis for.
That'd be very helpful.
Secondly, we have projects going on in the Department of Electrical Engineering at Pecan Street where we're going to align the charging of many electric vehicles with the West Texas wind at night. So that huge bar that you had that was basically equivalent from transportation to coal, that we could take that and basically convert it to West Texas wind because we have great alignment with when you charge your car naturally at night and nighttime wind. There's a huge advantage there. So it's a demand response aspect in mass scale that's a new opportunity that I think that you could include in the whole bucket of, because there's no one silver bullet.
No. There's another opportunity, and that is Mercedes is developing, using MOFs, a vehicle that runs off of a fuel cell. So it's essentially electric, but it uses hydrogen.
And the Wheels analysis for that, when you get the hydrogen from natural gas, is nowhere near as good as natural gas power.
Unless you do it from sunlight.
What's that?
Unless you do it from sunlight.
Unless you do it from sunlight. Okay.
Thanks very much, everyone.
Thank you all.
Orbach.